Morning. So today we'll start our last part for dynamic routing protocols, part 3. In the first two parts, we discussed distance vector routing protocols. We focused on RIB, RIB, and EIGRB protocols as examples of distance vector routing protocols. And as we said in the first lecture, we have interior gateway routing protocols and exterior gateway routing protocols. Interior gateway routing protocols. The protocols run inside the same autonomous system. The exterior gateway routing protocols run between different autonomous systems. Inside the interior gateway routing protocol, we have two categories: distance vector routing protocols, which we start with and we discuss as an example RIB and EIGRB, and link state routing protocols, which we will discuss today. And the famous example or the well-known example of this protocol is shortest path, open shortest path first. So today we'll start the second category, which is link state routing protocols. In link state routing protocols, it's also known as shortest path first algorithm, and the famous algorithm under this category is the Dijkstra shortest path first algorithm. But Dijkstra or shortest path first algorithm, the main well-known routing protocols under link state routing protocols. What's the main idea of the Dijkstra algorithm? The Dijkstra algorithm aims at obtaining the shortest path to all destinations. So we need to calculate for each destination the shortest path to this destination. So to obtain or to get the shortest path, we first construct or generate weighted graph. So at the beginning, link state routing protocols generate weighted graph, and this weighted graph will contain all information or global information or global view of the network. And as we discussed, the main difference between the link state and the distance vector has a local view of the network, collect information from the neighbor, and the neighbor collect information from other nodes, and so on. So it doesn't construct global view. Unlike link state, in link state we generate global view of the network. So we construct a weighted graph. Each router will have a weighted graph or database that contains all nodes in the network and all links with all links and the cost for each link. So this weighted graph contains the main routers or the neighbors routers, all links between them, and we name it weighted because we put as a weight the cost of each link. This cost delay can be function of different parameters. But at the end, I see a link and a weight. This is what I can see in the Dijkstra algorithm. First, we construct weighted graph, and for me, the network contains the main routers and links between these routers and the cost of these links. That is the first step, is to construct or to generate a weighted graph. Then from this weighted graph, we obtain the shortest path or a minimum cost path to all destination. But for example, the shortest path for R2 to reach to R3, if I need to reach from R2 to R3, the shortest path will be from R2 to R1 and the cost 20. Then from R1 to R3 and the cost is 5. Then from R3 to the final destination and the cost is 2. So the total cost from R2 to any destination at R3 or after R3 is 27. If I try to reach to this destination with any other path, for example from R2 to R5 to R4 to R3, I will find the cost larger than this number. If I reach to this destination from R2 to R1, then R4, then R3, I will find also the cost is larger. For example, from R2 to R1, 20, R1 to R4, another 20, then from R4 to R3, is 10, so it's 50, and there is 2, there is 52. فالshortest path is 27 from R2 to R3 or any destination in R3. فالمين idea here or main يعني المين aim of a link state routing protocol is to first generate weighted graph that contains all routers with all links with costs, so it constructs a global view of the network. Then from this global view or from this weighted graph, we calculate the shortest path to any destination. Important note here, the shortest path not always, not in all cases, will be a minimum number, path with minimum number of hubs. Here we care about the total cost on the path, and we select the path with minimum cost or shortest path. It doesn't يعني it shouldn't be يعني it's not necessary to be the path with minimum number of hubs. البروتوكول اللي consider minimum number of hubs, which protocol that consider minimum number of hubs? الريب هو اللي consider minimum number of hubs. Here we choose the path with the shortest path or path with minimum cost. But in some cases, maybe I reach to a destination with 3 hubs, but the cost is minimum. And I can have another path with 2 hubs only, but the cost is high. So I will select 3 hubs, even if the number of hubs is larger, but the total cost should be less. So here I am caring about only the cost, not the number of hubs. And this is very important and very important trick. I can give you example. Shortest path contain larger number of hubs. So you have to select the shortest path from a cost point of view, not from a hub point of view, a number of hubs. Okay? Any question? Okay. The shortest path to all destination is not always the path with the least number of hubs. And here is an example. If we have this weighted graph, and we need to calculate at each router the shortest path to all other destinations. But here, this is the routing table of R1. If I am in R1 and I need to build routing table, so I need to construct the shortest path first tree. What do we name by shortest path first tree? Here at R1, I'm at R1, and I need to reach to R2, I need to reach to R3, I need to reach to R4, okay, and I can reach to R5 from R2 or from R2 or from R4. So this is 3. And I need to calculate the shortest path to each router. Because here I can reach, for example, to 4 from 2 paths. I am directly connected to 4, or I can reach to 4 from 3 to 4. But I need in the shortest path 3, I need to only put only one path to each destination with the minimum cost. But this is what we mean by the shortest path tree. Okay, we construct a tree. The root is the router. We need to construct router table on it. But this tree هتبقى at each router. Each router will build its own tree or its own routing table. And from this tree, I can construct routing table. خلاص. From first, I start by my router or router. I need to build the routing table here, and all the branches is all links or all other destination. So I need from the root or from my router to reach to all other destination with minimum cost. So here in this example, if I started at R1 or I need to build the routing table at R1, I will construct the minimum path. So from R1 to R2, what is the minimum path? The minimum path is direct link from R1. I need to reach to R2. So the minimum path is 20 plus 2. So the cost is 22. But this is the cost to reach to any destination at R2. I need to reach from R1 to R3. So the minimum path is 5 plus 2. So it's 7. I need to reach from R1 to R4. This is what I told you. The shortest path shouldn't, يعني not always will be the path with least number of hops. Because if I need to reach from R1 to R4, what is the path with minimum number of hops? ده ال shortest path. بس ال path with minimum number of hops 20. This path with minimum number of hops. There is another path which is R1, R3, R4, 5, 10, and 2, 17. This is the minimum cost path. So I will select the path with minimum cost, not the path, and it's directly connected to me. So it is only one hub. But I can reach to this destination by two hubs because these two hubs have minimum number of costs rather than a direct connection or a direct hub. Here, this if I need to reach to R4 from R1 to R4, I can select R3 then R4 because the cost here is 16. 5 plus 10 plus 2. If I need to reach to 5, so I will go from R1 to R3 to R4 then R5. 5, 10, 10 and 2. That's 27. By this method, I construct a routing table of R1. And routing table contains shortest path to all other destinations. From R1 to all other destinations. This is the routing table, or I can represent it represent this as a tree or shortest path tree. All this table about all this information will be broadcasted from R1 to all other routers because all other routers need to construct the global view. So all this table will then, after building this table at R1, R1 will forward this table to R2, to R3, and R4. And also, here now we'll come to it again. To construct also a global view, R4 will receive routing table of R1 and will forward it to R5 also. Unlike previous protocol can this router must receive the updates from R1 and update its routing table, then forward its own routing table. Now R4 will forward the routing table of R1 to R5 and the routing table of R4 to R5. But all all information or all routing table will be flooded or will be distributed or be sent to all nodes in the network. Why? To construct a global view of the network. Okay. This is the first step. Right. Step by step how we can we can construct or we can run this protocol. First we have link and we have link state. Here, for example, if I start by R1, I have, for example, this link. But this link is specific interface. فاللينك we name it a specific interface. This link refers to an interface on a router. R1, for example, here R1 has three interfaces or three output or three links connected to R1. That is three links or three interfaces. This is a link. A link state is the information of this link. So for example, I have this link or this interface. What is the link state? Link state is all information of this link. For example, IP of this link, the type of the network, the cost of this link, the neighbor routers that this link will connect it R1 to. But all this information is, we name it a link state. So we have for each router number of output links or number of interfaces, and each link carry some information like IP, like cost, like the destination or the neighbor routers. All this information we name it link state. So we have link and link state. Okay. And at the beginning, link state routing protocol use hello protocol, and we discussed this hello protocol before. Hello protocol sending hello packet to the neighbor. And what is the the main the main purpose of this hello protocol to discover the neighbor and make sure that the neighbor routers are still alive. So every now and then we exchange hello packets to to make sure that the neighbor routers are still alive. Okay, and also at the beginning to discover a neighbor's routers. Each router is responsible for saying hello to its neighbor on directly connected network. So this hello packet will be exchanged between each router and neighboring routers. Okay, this at the beginning hello packets to discover or to make sure that all neighbor routers are still alive. So the purpose of hello protocol to discover a neighbor that uses the same link state routing protocol on this link. So for example, R1 need to discover that there is R2 and R2 and R1 using the same link state routing protocol. So and R3 and R4. So at the beginning, R1 will send hello packet, hello, I am R1, and will send it R2, R3, R4. Then R2 will reply, hello R1, I am R2. R3 will reply, hello R1, I am R3. R4 send back, hello R1, I am R4. So by exchanging this hello packet, R1 will make sure that its neighbor is R2 and R3 and R4 and all of them are still alive. That is the hello packet at the beginning. So connected interface using same link state routing protocol will exchange at the beginning hello packets. And once routers learn its neighbors, they form adjacency. So each two adjacent neighbor will exchange hello packet, and this packet will serve as keep alive function. So we exchange this packet to make sure that my neighbors are still alive. Okay. This as the beginning, as the initialization, and during during running the network to make sure that my neighbors is still alive. That is the first step is exchanging hello packets. So the first step, each router learn about its own directly connected network, and then it's responsible for saying hello to the neighbor and building and all collecting information about a directly connected network. Then second step, building link state packets. Each router will build a link state packet containing the state of each directly connected links. Now, after R1 knowing that there is R2 and R3 and R4 neighbors bit, it will collect information about the direct link. For example, here it's as link 1, link 2, link 3, and collect information about the link state or link cost about this link. So this information will put this information into a link state bucket. A link state bucket contains the main information of directly connected link. And I will exchange this link state bucket with the other routers. So I will collect information from with other routers to collect information or collect knowledge about the whole network. This information will be sent a link state bucket. Okay, a link state bucket contain state of each directly connected link and include information about neighbors such as neighbor ID, link type, link cost, bandwidth, and so on. So each router, after we say hello at the beginning and knowing that there what's my neighbor, I will exchange back actual information back will be used to build the routing table, which is link state bucket. So link state bucket contain information about a directly connected link. Is it clear? So at the beginning, I say hello. So I discover that and R1, R2 reply, R3 reply, R4 reply. So I know R1 that there is R2, R3, R4 directly connected to me. Then I collect information about the directly connected link to me. And then R1 connected to four links, collect information about the link cost, link IP, and so on. The link state, name it link state, and put all the link state or state of each directly connected link into a link state bucket and share this link state bucket with the other routers. Okay. So now after this step, R2 I will collect information, for example, about this information coming from R1 to R2 will collect information about this, R3 will collect information about this part, R4 will collect information about this part, and also when R4 share link state of packets about their own links, R1 will know that there is a link here, connect R5 by R4, will know that there is a link here, connect R4 by R3, and this link is already known. Okay? After exchanging link state packet, we يعني expand our knowledge. خلاص at the beginning R1 can only know its neighbor. Now after exchanging a link state packet, also we know some information about a large network or other other links or other nodes in the network. Okay, but this is very important. Each router build its own link state packet. Will link state packet contain information about directly connected link. This information can be neighbor IP, link type, link cost, and so on. Okay, clear? الفيرست ستيب hello exchanging hello packets. Second step exchanging link state packets. One difference between this link state protocol and distance vector protocol is flooding a link state packet to the neighbor. This is what I said to you from minutes. What do we mean by flooding link state packets? So instead of sending and the distance vector update now we apply so link state packets will we will do flooding for the link state packet. What we mean by flooding? Once a link state packet are created, they are forwarded to all neighbors. This is normal. I will forward the link state packet to my neighbors. After receiving a link state packet by the neighbors, it will forward it again to other nodes. But the same packet will be flooded and will be distributed or will be sent to all network. Then each router will receive this packet, extract information, update its own routing table, and forward this packet again to other nodes. All other nodes will receive the packet, update the routing table, and send to other nodes, and so on. So the same packet will be sent to all other routers in the network. This is what we mean by flooding link state packet. So we flooding link state packet means we create a link state packet, send it to the neighbor, and after receiving the packet at the neighbor, it will forward it to all other network. Each router floods the local state packets to all neighbor, who then store all link state received in database. And each router, once I receive these updates, I will store these updates in a database. We name it link state database. Okay. The third step فهتيسس يعني the first step again يعني to make the sequence to understand the sequence well. First step is hello, just to discover my neighbor. Then building a link state packet, putting all information about my directly connected link. Third, flooding this link state packets to all neighbors and all network in the network. So I am flooding this packet to all network, to all nodes in the network. After flooding this packet, I will construct a link state database. Each router will construct or use database to construct a topology map of the network. What we mean by link state database? Link state database of the topology or the network that we are considering. Here, each router will build a database that contains all information or all map about the network. This is what we mean by global view. For each router will build a database that contain all other nodes and all information about these nodes. After receiving link state packets دي طبعا coming from all nodes. For example, R1 will receive link state packet from R2, will receive link state packet from R3, will receive link state packet from R4, and also will receive link state packet from R5. Why? How R1 receiving link state packet from R5? What? Yes, exactly. Because we use flooding. R5 will send to R4 and R4 will forward this packet to R1. Each router will receive all link state packets from about all network. After receiving this packet, I will put this updates or this information into a database to construct the global view or the global map about the network on my own database. Each router will use database to construct a complete map or global view and compute from this map compute the best path to each destination. And once we have this map, we will apply as the first slide. We will select all destination and select the path to each destination. The best path or least cost path or shortest path to each destination. Once I build this global view or this database. This is the shape of the database. Here we still at the R1 as an example, and same repeated at each routers. R1 will collect information about its own directly connected link, R2, R3, R4. But this is the link state packet at R1 and will flood this to all other routers. At the same time, all other routers will also construct link state packet and flooding it to all other routers. R1 will receive from R2 the all connected routers to R2. R2 connected to R1 and connected to R5 and has host host IP اللي هو cost by 2. R2 this is the information or link state packet coming from R2 contain all information from R2. Once R1 receives this information, we'll put it into database. So that this is R1 database will contain all information about R2. Also all information about R3. Here R3 has R1, R3 connected to R1, connected to R4, and connected to local hosts by cost of 2. This information of R3. Also all information about R4, all information about R5, and my own information about R1. This is my own information. But this is the received link state packets containing all information about the all networks. Once it's received at R1, R1 will put this information into a R1 database, link state database. But this is the complete database I told you. This complete database contains the global view. Now R1 saying R2 say يعني can see R2, can see R3, can see R4, and can see R5, and can see all links with all costs. By building this database, I can easily I already constructed a global view or complete topology about the network. Okay, clear how to construct this database? Okay. From this database by digestra algorithm or shortest path algorithm, I can construct my own routing table. A routing table I contain only destinations and shortest path to this destination. After exchanging link state updates, we build a global or a complete database. And from this database, I can, using digestra algorithm or shortest path algorithm, I can construct a routing table. A routing table will contain destinations and shortest path to each destination. And we see we already calculated this shortest path to all destination, and we already built this routing table from this graph. As this graph represent a link state database, and from this graph I can easily obtain destinations and the shortest path and the cost to all these destinations. Any question? Do you know now what you need to know from here? Different steps. Hello. link state bucket generation, link state bucket flooding, constructing a database, then we reach to building routing tables. But these are the main steps of a link state routing protocol. Suppose that this protocol is يعني much easier than the previous parts يعني. Last part ده المفروض ان هو يعني much easier يعني. Okay? Any question? Okay. After building a routing table, we run a shortest path first algorithm and build a shortest path tree. This shortest path tree طبعا process begins by examining R2 information. I collect R2 information. Well, R1 already know it's connected to R2. So once I received information from R2, this information is already, I know that I am connected to R2, but in the database, I will include all information, even if the information I already knowing. Because database contain all information about all nodes. R1 already know that it's connected to R2, but also it gathers this information from R2 and put it in the database. Then we determine from this database, we determine the shortest path to destination by adding the cost and finding a lowest cost. Adding the cost of each link because I need to find the path from this router to the final destinations. So I accumulate all the costs and select a lowest cost. For example, this example, what we already calculated, if I need to reach from R1 to R4, so I will go to R1, R3, then R4. So I will add this cost 5, 10, and 2 and select the lowest cost. This is the shortest path first tree or how to construct a routing table. Once the shortest path first algorithm determines the shortest path route, these routes are placed in the routing table. And this is simple 2 steps. يبقى here in the steps we building a route a database at each router. Here the examples at router 1. This is a database. From this database, I run the shortest path algorithm to build the shortest path tree from this router to all destination within minimum cost and put this information or this shortest path routes into my routing table. This is the last step. From دي الستبس of link state routing protocols. طيب what are بقى characteristic or a requirement to use link state routing protocol? This requirement or characteristic. For example, from a memory requirement, يعني after you see the steps and how a link state routing protocol work. What is the requirement of a link state routing protocol? First, from a memory, it uses more memory or less memory? It needs or uses more memory. Why? Because of constructing a database. Building a database, I consume more memory because I need to build a complete database for all information about the network. Processing will also need more processing to build this routing table and to calculate the shortest path to every destination. I need more processing. The bandwidth, initially at the beginning, I need more bandwidth because I will exchange also or flooding because of the flooding. Flooding, I receive the data and flooding this data to all other nodes. So this flooding make I يعني consume more bandwidth at the beginning because of flooding and to exchange link state information and building routing tables. It consume more memory, it needs more CPU, and at the beginning it consume more bandwidth. But on the opposite side, or on the advantage, it converge very fast compared to distance vector. We discussed this last in the previous parts. It converge faster than a distance vector. Okay. Any question? Okay. So we can stop here.